Uncritically, and without really understanding Plato's arguments, they exalted the pure and the theoretical sciences, such as geometry and astronomy, and they looked down on any research that was mechanical or which had practical applications. This is what is known as the Dark Ages. There were other reasons for the lack of progress in the study of motion. Much of the most important of these was the absence of devices which could be used to measure short intervals of time, of the order of a few seconds. They had water clocks of various types, some of them capable of running for up to 24 hours or more, but when they were used for scientific measurements, like in astronomy, they did not measure the passage of time as such, nor were they calibrated in time units. I'll skip just a bit. Instead of having 24 hours of equal length, they divided the day, measured from sunrise to sunset, into 12 equal divisions, with the result that their hours were not fixed units of time and varied from what we would call about 40 minutes to about 80 minutes from summer to winter. This system was adequate and indeed rather useful for the time measuring needs of everyday domestic life. The working day for the ancients ended effectively at sunset. Sun goes down, can't see anymore, go to bed. And if one had to get through one's daily duties in less time in the winter, it's really just as sensible to have shorter hours as to have fewer hours. But for the astronomer, it carried serious problems. If he wished to fix a point of time at which an eclipse had been observed, right? Was it 2 in the afternoon or what? Midday? 6 p.m.? What was it? He had to specify the hour and also the exact time of year, and do quite a lot of arithmetic to correlate 2 points in time fixed by this method. Sticky. It was probably for this reason, more than any other, that our system of fixed equinoctial hours eventually replaced the classical system. Until that occurred, it was virtually impossible to subdivide the hour into minutes and seconds, which would likewise have varied in length according to the time of year. Minutes longer and shorter, and seconds longer and shorter, depending on which day it is. Truly daunting idea. There was, however, one smaller unit of measurement used in the law courts of Greece and Rome, which was to some extent fixed and regulated by law and did not vary with the seasons. In order to ensure fairness, the prosecution and defense were each allowed the same amount of time for presentation of their cases. The measurement was made by the simplest form of water clock, called a clepsydra, C-L-E-P-S-Y-D-R-A. It was a jar of fixed capacity, with a hole at its base of fixed diameter, through which the water ran away. The time was assessed in terms of 2 clepsydras, 5 clepsydras, and so on, according to the complications of the case, or in a civil suit, the amount of money at stake. There may have been some attempt to standardize this unit of time, since the surviving remains of 1 clepsydra in the Agora Museum at Athens bear 2 marks, which seem to indicate a check on its capacity by an inspector of weights and measures. A reconstructed model of this clock runs for about 6 minutes per filling. But this use of time measuring device was in the interest of fairness, not in the pursuit of science. The same might be said of another application of the same device, recorded in an anecdote concerning a well-known prostitute in 4th century Athens, who was known professionally as the clepsydra, because in order to ensure a fair distribution of her favors, she installed a water clock and timed her clients' visits by it. Now it talks about Archimedes a bit. Archimedes wrote a book called On Floating Bodies, and it is obvious, says the author within this book, it's obvious that he knew the earth was round. He knew the earth was a sphere. And here's the part. He goes on immediately to make clear that by on the same level, he means at the same distance from the earth's center, accepting without comment the conclusion reached by 4th century astronomers that the earth is spherical, and that the force of gravity acts towards its center. These ideas, so long familiar to us, cannot have been obvious to common sense or easy to assimilate. Now, it was regarded as knowledge of the geometers in ancient Greece. So there were geometers who knew that the Earth was moving, and that the sun was massive and huge and very, very far away, and that the moon was going around the Earth. They understood the whole relationship. 2,000 years before Columbus sailed the ocean blue, the Greeks knew that the Earth was round. However, this was largely disregarded, this knowledge, even by philosophers, because it was so obvious to common sense and to the five senses that we are not moving. We are not in motion. Everybody knew that. That was obvious, even though the geometers say we are. For example, if you have a pail of water, the Greeks knew something about this, or if you have a sling, they would be more familiar with that. A sling, and you put a rock in the end of it, and you just go like this or whatever, and the rock will just fall out. But if you swing it around, or take a bucket and swing a bucket of water around, the water stays in the bottom of the bucket, even when it's over up above, and the rock stays in the end of the sling, against gravity's say so, because of the swinging, the central fleeing motion. Now, there's centrifugal, I believe that means center fleeing, and centripetal, which means center attracted to the center, I believe. And the centrifugal forces, the center fleeing force, is what pushes the water down to the bottom of the bucket, pushes the rock against the sling. What if you were standing on the bottom of the bucket? What if you had a whole bunch of little people and little buildings on the bottom of the bucket now, outside, not where the water is inside, but on the outside, and then you start swinging that? What would happen to the people on the bottom of the bucket? They'd fly off. What if you took your rock and put it on the other side of the sling? Instead of inside of it, you put it on the surface on the outside and started swinging. It would just fall off. What if humans are on an Earth that is spinning? They would just fly off, obviously. So, not only that, but calculate the speed at which we would have to be moving. We would have to be moving, the actual speed we're moving is about 1,000 miles an hour. But the speed that they would have come up with would have been much, much slower than that, but it would have just astounded them. That the Earth has to be spinning and moving through space, just too much. It's just too much for them. So even though geometers knew it, it was just largely disregarded. It's just bizarre. So that was the view of but they knew this 2,000 years before Columbus sailed the ocean blue. The Greeks knew, the Greeks knew, the Greeks knew. Our information on Greek theoretical knowledge of mechanics comes almost entirely from two works: Mechanical Problems, attributed to Aristotle, but probably of a later date, written by a member of his school, and Hero's Mechanica. Mechanical Problems cover some of the same ground as Hero's Mechanica, pulley systems, the wedge, and the lever. Other than that, we don't have too much information about the Greek theoretical knowledge. Now it talks about the Greek achievement in chemistry and medicine, and it says that the Greek doctor could choose from an array of chemicals and stuff he had in his laboratory or office, but he didn't know exactly what was going to happen with each given one, and in the early days it was just experimentation. So this just randomly, how about this one, how about this one, how about this one? Now they had taken out the poisons. They didn't really use actively deadly poisons, but they still managed to kill people. But, quote, they were beneficial in some cases. All the doctor needed to know was the source of the material, the method of preparing it, and the dosage. And they would just try to get something that worked. They would do this, and did that heal the patient? Well, let's try this. This. In fact, chemical testing and analysis was for the Greeks almost entirely a matter of using the senses. Of the range of terms they used for what we would now call chemical properties, there is hardly one which does not relate to taste, smell, or touch. So in getting to know all their medicines and stuff, they really didn't have any scientific approach as we understand it. All of their knowledge and dealing with the medicines was